Hey everyone. There's been some questions about questions 2, 3, and 4 on Module 3, Project 3. And I kind of want to go over the basics of what we're looking at here, what this is trying to do. All of these involve the circular aspect of angle. So I'll look at Eratosthenes' problem here. And I'll get a little dramatic in my rendition of it here. Now, the idea for, and this is problem 2, where Eratosthenes solved, we'll make an assumption that the rays of the sun are in general parallel. So the rays of the sun are coming in and they're parallel. Let me draw a better parallel ray like this. Let me extend it out this way. And that's the assumption Eratosthenes made. Now he had this idea that when he read this book about the well at this one location and compared it to their location, this was 7 degrees and 12 minutes. Well, if we convert that, that's 7 degrees and 12/60ths of a degree, because there are 60 minutes in a degree, or 7 1/5, or 7.2 degrees. So they were able to measure that. Now, if these are coming in parallel, this angle and this angle will be the same due to the similar nature of the triangles. And what this sets up is a really neat thing. By walking this distance, Eratosthenes was able to measure the arc length of the circle. And their idea was, well, if I have this part of a circle and I know the degrees, well, in a full circle there's 360 degrees. And so they took this one part and said, if this is indicative of a circle and I have 7.2 degrees, well, if I divide these out, I find that, what I have my notes here, grab my calculator, that there are 50 of these all the way across the circle. And so if you know this arc length distance, this partial of the circumference, you can work out and figure the whole circumference of the Earth. And that's what Eratosthenes did. And so if you use this idea as a ratio, and the concept of angle being part of a circle, the arc length will determine the whole circumference. You can kind of set it up that the arc length that we have measured is r times the angle Eratosthenes measured. And the overall circumference is the radius times 360 degrees. If I divide these two equations, I get the ratio between the circumference and the arc length. Well, the r's will cancel out, is the ratio of the degrees. And when Eratosthenes did that, they got a really nice measure. Now it's in stadia, but I gave the conversion factor for stadia, and you'll find that they got within 1.2% of what we measure with lasers and satellites right now. But the idea in question 2 is if we think about angle as part of a circle. And I guess the big realization is the rays of the sun are kind of coming in parallel, and that we get these complementary angles between these. Or not complementary, Complementary is the wrong word. That's a specific type. We get equal angles due to the parallel nature of the light rays. And this worked out very, very well. The Greeks were able to measure by walking and the shadow the circumference of the Earth within 1.2% of the modern day measure. In fact, they're only off by 700 kilometers, which, when you think about the technology they used, is a pretty good measure. They were lucky. The area that they were measuring was relatively flat, so they didn't have hills messing with their distant measure. And when we say someone walked it, what Eratosthenes actually did is he employed someone who made maps. And so when they say walk it, that was them going out and surveying. So that should get you set up to work with question 2 on the project. Question 3 is a similar idea. We're looking at what we know about the Earth and the Sun. So the Earth travels around the Sun in this direction, looking down from the North Pole in the Sun. And it's roughly circular. And so we have a radial idea here. We have the radius, or the average distance to the Sun. And so as the Earth is rotating around, well, that is an angular momentum. It goes all the way around the Sun, 360 degrees, or 2 pi, in 1 year. And so if we think about how we talked about angular velocity, when we looked at it, we said that the angular velocity was equal to how much we changed in degrees over how much we changed in time. That was the definition we set up in class. And so we could think about this as going through 2 pi. So I do think I asked for it in radians. Let's see, yeah, radians per 1 year. And I gave an exact measure for years, 365.24 years. And so the big thing here is to convert your units, to convert this into seconds, and you'll get radians per second. Now the linear velocity, or how quickly the Earth would move if it didn't have gravity pulling in, or how fast it's going in the straight line, well, we said that the linear velocity is the radius times the angular velocity. So with this calculation, we should be able to figure out how fast the Earth is going in angular velocity, given it completes 2 pi radians in 365.25 days, not years. And then we need to figure out how many seconds are in a day to use the conversion factor to convert that to radians per second. And then if we multiply it by the radius, we'll get kilometers per second, and we can convert that to kilometers per hour. But the main equations we're using is our definition of angular velocity and our definition of linear velocity. Now what's neat is I'm going to put another circle here for the Earth. The Earth rotates about its axis, and it does that moving in this direction also. And so it moves east to west. So looking above the North Pole, it would travel in this direction. And it does that where it completes 2 pi in 1 day. So you can figure out the angular velocity that the Earth does in its own little rotation. And you can figure out the same thing, the velocity vector, by the radius of the Earth times its, so I'll say of the Earth, and we'll say about the Sun for these. These are about the Sun. Whoops, this one's of the Earth. And so there's a point in the day where the vector going this way and the vector going this way line up. And if we look at it on the Earth, it's when the Earth is here relative to the Sun. And these two vectors, when they come together, well, we can add this velocity and this velocity. So that's how fastest a point on the Earth is moving relative to the position of the Sun. And so this question focused on the definition of angular velocity and its relationship to linear velocity. We just have two circles moving that we keep track of. And so the fourth question is doing a similar thing. It's going to look at the hands of a clock. And so I have two hands of a clock here. I have the minute hand and I have the hour hand. And they're going to move with the minute hand moving faster. And so we can think about the angular velocity of the minute hand. Well, it goes through 2 pi every 60 minutes. It works its way all around in 60 minutes. While the angular, let me make this the minute hand. And the angular velocity of the hour hand, I should have color-coded these to match, of the hour hand goes through 2 pi in 24 hours, or 12 hours, sorry. The hour hand goes around in 12 hours. So the motion that we get out of this, as it moves around the clock, these two things will start moving. This will start moving forward, and this will start moving forward. Now, the hour hand is going to go all the way across, and then plus a little bit more, or the minute hand. Sorry, the minute hand will go all the way across and plus a little bit more in the time it takes the hour hand to move forward a bit. And so the angle that the hour hand goes through will be 2 pi plus some, I'll just put a prime on it. And because the hour hand is moving with an angular velocity, which is the change in theta over the change in time, well, if I multiply it by time, I'll get the theta. And so we can look at how far the hour hand moves in a given amount of time. But what we want to be equal is this angle here. So what we'll also notice, let me correct myself here. This is the minute hand. The minute hand is the faster moving thing. It'll go all the way around. It goes around in 1 hour and a little bit is really what I want to say. The hour hand is the slower moving one, and it's going to total some theta prime. And so what we can do is we can solve for when these two things equal. So what we need to figure out is how far they move, and then set them equal like this. And so we look at the angular velocity of the hour hand times the time, which is the thing we don't know, is going to equal theta prime. And the angular velocity of the minute hand times the time, which is the thing we don't know, is going to equal theta minute. And so we take theta prime here and substitute it into here, and so we're going to get 2 pi plus this. And what we want to do is we want to solve for t. And so this is again the concept of circular angle, and realizing that the faster thing, which I keep flipping around when I say it, but the minute hand moves faster than the hour hand. And so the setup we have if we're solving it for actual numbers, is the minute hand moves 2 pi in, and I think seconds will be the better thing to do here. If I look at my notes, I solved it in seconds. And so in this moves 1 hour's worth, or 3,600 seconds, times time. And so that's that part of the equation. And then 2 pi plus, well, the hour hand moves 2 pi, and it takes 12 hours to move around. So it's 12 times this number, which is 43,200 seconds in 12 hours, times time. And so what you want to solve for is the time here. And so all three of these questions focus on the circular nature of angle. This one's static, it's not moving. This one uses the definition of angular velocity and linear velocity. And this one uses the idea that you have two things that will repeat on a surface. And the repetition happens after 2 pi. So those are the core of those problems on the notebook that I wanted you to be thinking about the circular definitions, because we'll see when we do simple harmonic motion that circular nature really talks about what we mean by angular velocity, and we'll see later angular frequencies.